this lecture, we will discuss the Magee-Boodman algorithm. It is a model used for production planning, both at an aggregate level and for materials management, derived from inventory management models. In particular, it is a multi-product variant of the economic order quantity model, working under similar limiting assumptions, namely stationary demand and one single production resource. Objective of the model is to determine the economic length of the production campaign by calculating the optimal number of production campaigns to be realized in the planning horizon. In every campaign, all the products are produced in the same order and in the same quantity. Let's introduce the relevant terminology. N0 is the number of campaigns performed in the planning horizon. K is the product index. H is the number of working days in a year. RK is the production rate for product K. DK is the annual demand for product K, which is constant during the year. CM is the stock holding ownership rate. PK is the variable production cost of product K. AK is the setup cost faced to start the production of product K. The setup cost coefficients AK do not take into account time of lost production, and they do not depend on the production sequence. In case of sequence-depending setup costs, it is necessary to predefine the optimal sequence using specific algorithms aimed at minimizing the total setup costs and keep the sequence fixed in all the campaigns. The total stock holding costs are given by the following formula, taking into account for every product K, variable production cost times stock holding cost times demand times the coefficient considering a finite production rate divided by 2 divided by the number of campaigns or production lots in a year. Under the hypothesis of predefined production sequence of all the products, the total setup cost is simply obtained by summing all the setup costs for all the products and multiplying these times the number of campaigns in a year. Notice that N0 does not need to be an integer number. In case of, say, N0 equals 2.5, we know we will be carrying out 5 production campaigns in 2 years' time. By summing up all the costs, taking the first derivative with respect to N0, equaling the derivative to 0, and solving the equation with respect to N0, the optimal number of campaigns is obtained as follows. The similarity with the EOQ formula in case of a finite production rate is manifest. So, the economic quantity to produce in every campaign for the product K is simply obtained dividing the total yearly demand times N0. As an example, if the total demand for product 1 is 2500 pieces and N0 equals 2.5, then Q0 for product 1 would be 1000 pieces. Some issues for an effective application of the model should be carefully considered. Degenerate campaigns, uncertainty of demand forecasts, setups dependent on the sequence, capacity constraints, and setup times. Degenerate campaigns it is not always worthwhile to produce in every campaign products characterized by small demand and high setup costs. In this case, it is suggested to proceed as follows. Calculate the economic order quantity, QK, of each of these products considered separately. If QK is much larger than Q0K, consider producing product K by alternating or occasional campaigns. The costs associated to the different alternatives are calculated, and the solution with the lowest total cost is chosen. In case of uncertainty in demand forecasts, adequate safety stock shall be used. As previously mentioned, in case of sequence-dependent setups, because there is no constraint on the sequence due to the campaign, the optimal sequence is chosen before the application of the model, and then the optimized setup costs obtained with such sequence are used. How can the model take into account setup times and capacity constraints? A graphical representation of the optimal number N0 could help. Let's draw a graph having on the horizontal axis the total demand, expressed in equivalent units, and on the vertical axis the total number of campaigns. The shadowed area represents the admissible zone. That is, in that area, the total production time plus the total setup time do not exceed the available capacity. Any point over and above that area would result in an unfeasible solution, causing a potential loss of demand. Let's then draw the N0 curve, which, by considering the previously discussed formula, is growing with the square root of demand. If the value of N0 found out by applying the formula is within the admissible zone, then production capacity is not an issue, and the company can proceed running exactly N0 campaigns per year. On the other hand, should N0 be over and above the admissible zone, then the total required production plus setup time should be reduced by diminishing the number of campaigns down to the point in which N0 meets the limit of the admissible zone. A lower number of campaigns will imply lower total setup time and, consequently, a feasible plan.